Now, I've been having some technical difficulties. However, we go on. So, our second wind equation is going to work from the period of time uh, on which from which the adapter first hits the bungee cord to where the adapter pushes the bungee cord back as far as it will go before coming back, or coming to a rest rather. So I discovered that for our purposes, it would be best to estimate K as 40, although that is in reality a bit large. This is not exactly the most realistic of circumstances. This is more just to show the theory and the possible applications of this one equation. So we have our wind equation, and I already showed you what we do not need for this case, and that would be the final velocity here, because the adapter will stop moving in the end of this time period. There will be no velocity, and we have no change in potential energy during this time period, as well as no work due to friction. And initially, the elastic cord is not displaced at all. So that leaves us with initial work equals 0 equals negative 1/2 m initial velocity squared plus 1/2 k displacement squared. And then we can eliminate the 1/2s, and we get mass times velocity initial squared equals kxf squared. And we can plug in some numbers here. So m 0.05 times 1.98 squared equals 0.5 equals 40, because we changed our spring constant here, times x of f squared. So now we can plug it into this equation for x of f, which would be equivalent to square root of 0.05 times 1.98 squared over 40. And that would come out to be 0.07 meters, or about 7 centimeters. Now, you might ask what the importance of this would be. Well, let's say that rather than an adapter, this was a real person on a thrill ride in an amusement park, and they were swung into a cord to catch them. We can't have the cord being displaced too much due to too much velocity at the point of impact. Otherwise, it could snap, and then the park owners would likely have a lawsuit on their hands. So that is the possible application of this. That concludes my final video. Thank you.